we are counting down the 10 most unsettling scientific anomalies that make 3I/ATLAS, the newest interstellar visitor to our solar system, far more mysterious and potentially more alarming than anyone could have imagined. From impossible measurements and unbreakable physical resilience to data blackouts and startling theories of artificial origin, each anomaly in this list exposes a deepening web of enigmas that defy everything astronomers once believed about comets, cosmic debris, and interstellar travelers. These rankings are derived from the latest October findings, which have not only stunned researchers but have also shifted 3I/ATLAS's probability of being non-natural from mere speculation to a mathematical likelihood that is deeply uncomfortable to dismiss. As of the newest analyses, the odds of 3I/ATLAS behaving like a typical comet are estimated to be less than 1 in 10,000, according to independent models from observatories tracking its light curve and spin rate. So, which anomaly eclipses all the rest? Let's find out, starting with number 10. In 10th place, 3I/ATLAS delivers a measurement so bizarre it has left comet scientists genuinely unsettled. A negative polarization reading of minus 2.77% at a phase angle of 6.4 degrees. Normally, when sunlight scatters off the dust in a comet's coma, the polarization of light shifts in a positive direction, typically ranging between plus 1% and plus 25%, depending on dust size, angle, and composition. But 3I/ATLAS has broken that rule entirely. A negative polarization suggests the light is scattering in a backward phase-inverted pattern, something seen only in ultra-smooth metallic or highly processed materials, not in natural icy dust grains. This anomaly implies that 3I/ATLAS's surface may contain nano-layered or metallic compounds, possibly similar to nickel-iron alloys found in spacecraft heat shields or meteorites that have undergone extreme processing. If confirmed, it would mean that part of the comet reflects light as if it were engineered, a detail that has astronomers rechecking every assumption they once held about its origin. That's the rule for every comet ever studied, until now. For 3I/ATLAS, the light doesn't just scatter differently, it comes back polarized in the opposite direction. This bizarre inversion has never been documented in any other comet, interstellar or otherwise. The moment the data was confirmed, the discovery set off a global scientific race. Multiple observatories independently verified the anomaly, and within hours, research teams from NASA's Goddard Space Flight Center, the Max Planck Institute for Solar System Research, and Japan's National Astronomical Observatory (NAOJ) began trying to replicate the polarization effect under controlled laboratory conditions. They used every known analog for cosmic dust, micron-scale silica, carbonaceous chondrite material, and even metallic inclusions. But every single experiment failed. No combination of particle size, geometry, or mineral composition could reproduce the strange polarization profile detected from 3I/ATLAS. Computational models suggested that to achieve a negative 2.77% polarization at 6.4 degrees, the scattering medium would need to be made of nanostructures smaller than 50 nanometers, possibly aligned in repeating lattice-like layers, a configuration unseen in natural comets. The implication was both simple and deeply unsettling. The dust surrounding 3I/ATLAS might be composed of materials or structures unknown anywhere else in the solar system. To put this into perspective, over 4,000 comets have been cataloged and observed since the early 18th century, yet not one has ever produced a negative polarization signature of this kind. The discovery now stands as the first major warning sign, evidence that something about 3I/ATLAS's material composition is fundamentally beyond current scientific understanding. And if that wasn't disturbing enough, the 9th anomaly only deepens the mystery. Because when it comes to surviving solar activity, 3I/ATLAS defies everything we know about the fragility of comets. On January 27, 2025, the Sun unleashed one of the most powerful coronal mass ejections, CMEs, of the current solar cycle, an immense burst of magnetized plasma traveling at nearly 2,000 kilometers per second. Its target, the newly arrived interstellar object 3I/ATLAS. For most comets, a direct collision with such a solar storm would be catastrophic. These events typically release the energy equivalent of 10 billion hydrogen bombs, blasting out streams of high-energy protons and electrons that can strip a comet's coma, destabilize its tail, and in many cases obliterate the nucleus entirely. But not this time. When the CME slammed head-on into 3I/ATLAS, astronomers braced for the familiar pattern, an abrupt increase in brightness, jet eruptions, or visible fragmentation. Instead, nothing happened. Observatories from Chile, Hawaii, and space-based solar monitors all recorded the same astonishing result. 3E/ATLAS emerged almost completely untouched. Post-event analyses showed no measurable change in its brightness, structure, or trajectory. Its coma remained stable and diffuse, its tail unchanged, and its nucleus showed no sign of fracturing or material loss. Even its orbital path held perfectly steady, an almost impossible outcome given the sheer kinetic pressure of a CME impact, estimated at nearly 5,000 newtons per square meter at that distance from the Sun. To put that into perspective, comets like ISON 2013 and Enski, both significantly larger than 3E/ATLAS, were torn apart or vaporized under much weaker solar events. Yet this interstellar visitor absorbed the full brunt of the blast as if it were built to endure it. Such resilience is virtually unheard of even among the most durable long-period comets in our solar system. For an interstellar object, it's unprecedented. The survival of 3I/ATLAS through direct solar assault suggests one of two possibilities. Either it possesses an exceptionally dense metallic core with internal tensile strength exceeding 10 megapascals, or its structure is unlike anything formed through natural accretion. Either way, this anomaly points toward a nucleus engineered or evolved to withstand cosmic extremes that would destroy any known natural body. And that brings us to number 8, where the mystery surrounding 3I/ATLAS deepens even further. The physical features of 3I/ATLAS break nearly every rule in the cosmic playbook. High-resolution images from both the Hubble Space Telescope and Earth-based observatories reveal something astonishing, a nucleus that defies all known cometary shapes. Instead of the typical round, irregular, or potato-like form, 3I/ATLAS appears elongated, stretched into a slender silhouette reminiscent of 1I/Oumuamua, the first confirmed interstellar visitor detected in 2017. But the differences don't end there. Unlike traditional comets that trail a brilliant sweeping tail sculpted by solar radiation, 3I/ATLAS surrounds itself in a dim, ghostly haze, a diffuse ionized gas coma that refuses to organize into the graceful arc scientists expect. Spectroscopic scans from Hubble, ALMA, and Japan's Subaru telescope reveal unusually high concentrations of cyanide CN and carbon monoxide CO, both glowing faintly in ultraviolet and blue-green wavelengths. In normal comets, these molecules are mere trace compounds, but in 3I/ATLAS, their relative abundance is nearly 4 times higher than the mean value observed in long-period comets from the Oort cloud. This intense chemical imbalance hints at something much stranger. The overall emission spectrum doesn't resemble that of an icy primordial body. Instead, it bears similarities to oxidized regolith, the type of mineral-rich material found on the surface of Mars or other rocky worlds exposed to extreme radiation. Even more puzzling is the behavior of its coma. Instead of expanding outward as solar heat vaporizes the surface, the surrounding gas cloud remains tightly bound, suggesting electromagnetic cohesion or active containment. Researchers at the European Southern Observatory propose that the object may generate a localized magnetic field, a feature never recorded in any known comet. The nucleus itself remains difficult to isolate. Its core is partially obscured by the surrounding ionized haze, but advanced image reconstruction reveals a distinct asymmetry, a cigar-like or spindle-shaped body roughly 480 meters long and 60 meters across, with a rotation period estimated at about 12 hours. That gives 3/ATLAS a length-to-width ratio of nearly 8:1, far exceeding the 5:1 ratio observed in Oumuamua and well beyond the threshold of any naturally fractured rock known in the solar system. In short, 3I/ATLAS doesn't just look unusual, it's architecturally alien. Whatever forged this object, it wasn't the gentle gravitational dance that forms ordinary comets. It appears to be something built, sculpted, or shaped by forces we still don't fully understand. The chemistry and structure of 3I/ATLAS taken together refuse to fit into any known category in the cometary catalog. Its spectral fingerprints, composition, and morphology don't resemble any natural object previously recorded. Instead, they point toward a body with a unique history, and possibly an origin unlike anything that has ever entered our solar system before. The mass and trajectory that shouldn't exist. The mass and orbital stability of 3I/ATLAS have become one of its most perplexing mysteries. Based on brightness curves, gas production rates, and reflective modeling, scientists estimate the object's total mass to be around 3.3 times 10 to the power of 13 kilograms. That's over 73 trillion pounds, making it roughly 6 million times heavier than SpaceX's Starship and nearly 10 times the mass of comet Hale-Bopp, one of the largest ever recorded. But it's not the size that baffles astronomers, it's the way it moves. Despite continuous outgassing at rates exceeding 200 kilograms per second, which should act like miniature rocket thrusters and gradually push the object off course, 3I/ATLAS remains astonishingly stable. Astrometric data from Hubble, the James Webb Space Telescope, and a network of ground observatories across limits, less than 10 to the minus 8 meters per second squared, essentially undetectable. In standard comet physics, that's impossible. When a nucleus vents gas at hundreds of kilograms per second, Newton's third law dictates that the recoil should alter its trajectory, much like a leaking rocket veering off course. Yet 3I/ATLAS shows no measurable deviation whatsoever. To explain that level of inertia, models require a nucleus of extreme density and cohesion, a core capable of absorbing recoil forces without any noticeable drift, miles per hour, about 55 kilometers per second. Researchers have tested alternative explanations: perfectly symmetrical outgassing, rotating jet alignment, or coincidental balancing of opposing forces. But the probability of such perfect equilibrium is astronomically small, less than 1 in 10 to the 7th according to NASA's Jet Propulsion Laboratory simulations. That leaves one unavoidable conclusion: 3I/ATLAS is dense, cohesive, and built to endure motion through the solar system without disruption. In other words, it behaves less like a comet and more like a designed object. The improbable origin. If its motion is a riddle, its origin is an outright paradox. Asteroids and icy bodies ejected during planetary formation. Statistically, interstellar visitors should be common. Estimates predict that our solar system should encounter one such object every year, most of them small, faint, and fast. Yet, the record is almost empty. Before 3I/ATLAS, only 2 confirmed interstellar objects had ever been observed. One, I/Oumuamua in 2017. Both were tiny in comparison, mere specks compared to the colossal mass of 3I/ATLAS. According to population models from the Harvard-Smithsonian Center for Astrophysics, if an object this massive could drift into our system, statistical probability dictates that thousands of smaller interstellar fragments should have preceded it, but telescopic surveys, covering over 95% of the observable sky down to magnitude 22, have found nothing. This gap has forced astronomers to rethink the very foundation of interstellar population theory. Either our models are fundamentally flawed, or 3I/ATLAS did not originate from the random scattering of debris between stars. Some researchers now propose it may have been ejected deliberately, or perhaps formed in an environment alien to known astrophysical processes, a region where density, magnetic forces, and radiation could forge materials and structures unseen in any natural body to date. Whatever its true birthplace, one fact is undeniable: 3I/ATLAS does not fit anywhere in our current understanding of how the universe builds and moves its celestial wanderers. Before 3I/ATLAS, only 2 interstellar visitors had ever been confirmed: 1I/Oumuamua and 2I/Borisov, both smaller, lighter, and fleeting. But 3I/ATLAS changes everything. Its sheer scale and mass, combined with its solitary arrival, defy every expectation of interstellar statistics. According to planetary dynamicists, the odds of such a massive object emerging from the galactic disk without a companion swarm of smaller debris are vanishingly low, on the order of 1 in 10 to the power of 9. Simulations conducted by research teams at Harvard, MIT, and the European Space Agency's Near-Earth Object Program showed that the interstellar medium simply lacks enough dense rocky material to produce a traveler of this magnitude through random ejection alone. Even after adjusting for detection bias, the fact that our telescopes are more likely to detect larger, brighter bodies, our surveys should still have recorded a cascade of smaller interstellar fragments entering the solar system ahead of it, yet none have been found. Statistically, we should have seen hundreds, if not thousands, of smaller interstellar pebbles or icy shards. The absence of any supporting population is a glaring contradiction, one that challenges not only comet ejection physics, but also the entire theoretical framework of how planetary systems shed material into interstellar space. For 3I/ATLAS, the numbers simply don't add up. The deeper astronomers dig, the more the mystery expands, as if this object isn't part of a random cosmic population at all, but rather a singular traveler, deliberately alone. The timing and trajectory anomaly. Then came the anomaly that truly stretched belief to the breaking point. Extraordinary coincidence. But the details behind that passage have driven orbital analysts into heated debate. The trajectory wasn't random. As 3I/ATLAS entered the inner solar system, its inbound vector aligned within 0.02 degrees of the ecliptic plane, the precise plane where most of the planets orbit the Sun. For natural interstellar bodies, this alignment occurs in less than 0.0003% of cases. Even more astonishing, the object's closest approach to Mars occurred almost exactly 1 Martian year after the planet's previous solar conjunction, when Mars and the Sun line up relative to Earth. In other words, 3I/ATLAS arrived on schedule, matching a cycle that only a few orbital models could have predicted. If this timing were the result of chance, the odds are roughly equivalent to flipping a coin 25 times and getting heads every single time. To many astronomers, that's too neat to dismiss. The object's entry vector, solar approach speed, and gravitational deflection angles suggest an intentional trajectory, or at least one influenced by forces we don't yet understand, whether guided by unknown interstellar dynamics or something far stranger. 3I/ATLAS appears to have navigated the solar system with uncanny precision, and that's where anomaly number 5 begins to cross the line from cosmic curiosity to a mathematical impossibility. A near miss on a cosmic scale. But the coincidences don't end there. On March 16th, 2026, 3I/ATLAS is predicted to sweep past Jupiter, threading a trajectory that remains within just 5 degrees of Earth's orbital plane, a razor-thin corridor of space that most interstellar objects never even approach. Each of these planetary encounters, first with Mars, then with Jupiter, is precisely timed and geometrically consistent as if part of a deliberate sequence. According to Monte Carlo simulations run by orbital dynamicists at the Jet Propulsion Laboratory and the European Space Operations Center, the probability of this alignment occurring by random chance is less than 1 in a million. In these simulations, millions of virtual interstellar bodies were launched through the solar system at random orientations. Almost none, fewer than 0.0001%, produced the same series of near alignments along the ecliptic plane that 3I/ATLAS follows so perfectly. The precision is staggering. Even a single degree of deviation during its inbound phase would have diverted the object millions of miles away, sending it past the solar system entirely or altering its timing so drastically that neither the Mars nor the Jupiter encounters would occur at all. Yet, somehow, 3I/ATLAS maintains a trajectory that threads every gravitational needle in its path. To put that in perspective, most known interstellar objects, such as Oumuamua and Borisov, entered the solar system at steep inclinations, typically between 20 degrees and 80 degrees relative to the ecliptic plane. Their paths were random, chaotic, and unrepeatable. But 3I/ATLAS travels almost perfectly flat, as though it were navigating a predetermined route mapped out long before its arrival. This improbable choreography has ignited heated debate within the astronomical community. Some researchers suggest that unknown galactic gravitational effects, perhaps subtle resonances from the Milky Way's dark matter halo, could be influencing its course. Others have dared to ask a far more unsettling question: could the trajectory be more than coincidence? As the next planetary encounters draw near, observatories across the world, from Mauna Kea to the Atacama Desert, are preparing to watch. Every degree of motion, every subtle change in velocity will be scrutinized. Because if 3I/ATLAS passes Jupiter exactly as projected, without deviation, it would mark one of the most statistically impossible trajectories ever recorded in celestial mechanics, and for some scientists, that would make 3I/ATLAS not just a visitor from beyond the stars, but a messenger with intent. As anticipation builds, not only for the unprecedented data these encounters might deliver, but also for what their uncanny precision could reveal about the object's true nature, a new chapter of mystery begins to unfold. The NASA data blackout. Between October 1st and 4th, 2025, as 3I/ATLAS closed to within 18 million miles of Mars, something inexplicable happened. NASA's Deep Space Network, DSN, the communication lifeline for every interplanetary mission, went completely dark. Public access to telemetry feeds, signal logs, and live tracking dashboards abruptly vanished. Officially, NASA cited budgetary constraints resulting from a government funding lapse in Washington, D.C. But for many in the astronomical community, the timing couldn't have been more suspicious. Inside the DSN's command center in Pasadena, California, Flight Director Monica Valdez and her operations team reportedly shifted into restricted access mode, invoking security protocols rarely used outside of national defense emergencies. Internal logs later revealed a spike in classified communications, along with multiple encrypted data transfers to off-site archives between October 2nd and 3rd, precisely when the object made its closest pass. For outside researchers, universities, and amateur observatories, the blackout was catastrophic. It silenced every real-time tracking source at the moment the world was most eager to observe 3I/ATLAS as it intersected Mars's orbital path. Requests for transparency flooded NASA and JPL under the Freedom of Information Act. The questions were simple yet chilling. What did the Mars orbital sensors detect during the blackout? Why were DSN feeds cut simultaneously across 3 continents? And what exactly required classified handling during a publicly funded observation? None of these inquiries received clear answers. In one internal memo, later leaked to the media, a systems engineer described the period as an unplanned signal containment window due to telemetry, interference beyond expected spectral range. That vague explanation only fueled speculation further. Some scientists argued it was merely a technical coincidence, a product of bureaucratic timing and software maintenance. But others began connecting dots between the blackout, the trajectory anomalies, and a mysterious low-frequency radio echo that had reportedly been logged by an independent observatory in Chile just hours before DSN went offline. Was NASA hiding something, or did 3I/ATLAS itself, through electromagnetic interference or something else entirely, trigger the emergency protocols? The operational chaos magnified every previous anomaly, transforming what began as a scientific puzzle into a global flashpoint for conspiracy theories. Online forums exploded with speculation ranging from alien signal suppression to classified defense detections. In the aftermath, analysts at MIT's Lincoln Laboratory published a study showing that even a 12-hour gap in public telemetry during a critical flyby can lead to weeks of uncertainty in trajectory modeling. The 4-day blackout, therefore, wasn't just inconvenient, it effectively erased humanity's most detailed window into the object's near-Mars passage. And when data finally resumed, 3I/ATLAS appeared slightly off course by less than 0.02 degrees, but enough to raise eyebrows. No official explanation ever reconciled what happened in those silent hours, but for many, the blackout marked a turning point. It wasn't just about missing data anymore, it was about trust, control, and the possibility that someone, or something, was deciding what humanity was allowed to see. When mysteries reach this scale, every explanation feels inadequate. Yet, one theory, both audacious and unsettling, has begun to gain traction among researchers and theorists alike: the Trojan horse hypothesis. What if every anomaly of 3I/ATLAS isn't an accident, but a feature? Imagine an interstellar probe designed to masquerade as a comet, quietly threading its way through the solar system under the cover of cosmic routine. The trajectory alone demands attention. Aligned within just 5 degrees of the ecliptic plane, 3I/ATLAS has executed planetary flybys that would make celestial mechanics textbooks blush. Its encounters with Mars and Jupiter fall so precisely within a narrow orbital corridor that the statistical odds of this happening by random chance have been estimated at less than 1 in a million. For a natural body, such precision is an accident of gravity. For an engineered vehicle, it's a flight plan. The route would allow maximum data collection from key planetary systems, Mars, Jupiter, and Earth, while maintaining minimal visibility to deep space sensors. Then comes the question of resilience. On January 27, 2025, the Sun unleashed one of the most powerful coronal mass ejections, CMEs, of the decade. The plasma storm blasted through the inner solar system at nearly 2 million miles per hour, carrying enough electromagnetic energy to fry unshielded satellites and distort Earth's magnetosphere. 3I/A-TLAS took a direct hit, but instead of fragmenting, venting, or losing luminosity, it sailed through almost untouched. Spectroscopic readings from the Solar and Heliospheric Observatory, SOHO, indicated a nearly constant albedo. Its reflective signature didn't dim, even as solar plasma washed over it. The coma, normally a comet's most fragile feature, remained eerily stable. For a typical comet composed of volatile ices and porous rock, such an encounter would have been catastrophic. Some theorists have suggested that this is not coincidence, but intentional engineering. A vessel tough enough to survive solar radiation, micrometeorite impacts, and magnetic turbulence, yet camouflaged in dust and ionized gas, mimicking a natural comet's behavior perfectly. The timing of the NASA data blackout, just as 3I/ATLAS made its Mars flyby, only deepens the intrigue. Although no official report acknowledges any classified evaluation, quiet whispers within aerospace and defense circles hint that agencies were indeed modeling artificial body scenarios during the communications gap. There's a logic to it. The object's remarkable stability, its negligible non-gravitational drift, despite high outgassing, and a shape profile faintly reminiscent of Oumuamua, all converge toward one unsettling possibility. 3I/ATLAS might not be a mere rock. It could be a survey instrument optimized to observe planetary systems, not to be observed by them. If this were reconnaissance, it's the most elegant route imaginable. Now, as its closest approach to Earth draws near, observatories from Hawaii to Chile are on alert. The next series of observation windows could determine whether this is simply nature showing off its randomness or something else entirely, a Trojan horse built by intelligence we've yet to understand, moving silently through the light of our own star. If 3I/ATLAS truly is a Trojan horse, a disguised visitor from beyond the stars, then humanity's one chance to uncover its secrets is slipping away with every passing day. The final window. The countdown has already begun. On October 3rd, 2025, both Mars Express and ExoMars Trace gas orbiter turned their instruments toward the strange intruder as it swept past Mars at a distance of 18 million miles. A blink, cosmically speaking. Using onboard Nomad spectrometers and optical imagers, both spacecraft recorded the faint spectral fingerprints from 3I/ATLAS's coma, the thin veil of gas and dust that surrounds its core. These readings captured unusual emission lines, especially in the ultraviolet range, where the spectral ratios of cyanide CN and carbon monoxide CO didn't match any previously studied comet. Early comparisons suggest molecular structures that may contain complex organosilicon compounds, hinting that its chemistry could be non-primordial, possibly altered by artificial or high-energy processes. But the most anticipated opportunity still lies ahead. As 3I/ATLAS races toward the outer solar system, the European Space Agency's JUICE spacecraft, originally designed to study Jupiter's icy moons, finds itself in a once-in-a-lifetime position. By sheer celestial coincidence, JUICE's trajectory will carry it within 0.4 astronomical units, roughly 37 million miles, of the comet's projected path in early 2026. Mission engineers are now quietly debating whether to retarget JUICE's cameras and spectrometers for an impromptu observational campaign. If approved, JUICE's UVS spectrograph and JANUS optical camera could deliver the first high-resolution spectra and images of an interstellar object near Jupiter, data no other spacecraft can obtain. It's a daring proposition. Reprogramming a billion-dollar spacecraft mid-mission carries risk. But so does doing nothing. This might be our last best chance to understand what 3I/ATLAS really is. Meanwhile, ground-based observatories are mobilizing worldwide. Facilities like ALMA in Chile, Keck Observatory in Hawaii, and the Very Large Telescope VAL-T are coordinating a synchronized global watch through the winter of 2025 to 2026. Using advanced polarimetric filters and adaptive optics, they're scanning for last-minute anomalies, unexpected jets, rotational changes, or electromagnetic emissions that could reveal the comet's internal structure. The clock is ticking. On December 19, 2025, 3I/ATLAS will make its closest approach to Earth, 167 million miles away, about 1.8 times the distance to the Sun. After that, it will accelerate outward at nearly 55 kilometers per second, leaving the reach of all current or planned missions. Once it's gone, it's gone. Lost to the interstellar void, its mysteries carried beyond the range of human instruments, perhaps for centuries. And so, astronomers now race against time itself. Mars Express and ExoMars teams are still sifting through terabytes of spectral data, looking for chemical asymmetries or radio anomalies that might hint at something beyond the natural. The Global Observing Network, from the Atacama Desert to the Himalayan Plateau, continues to log every photon, every subtle flicker of reflected sunlight, hoping to catch one last revelation before the darkness closes in. This is the final window, a narrowing aperture through which humanity may glimpse either the most exotic natural object ever found or the first confirmed artifact of intelligence beyond Earth. Once 3I/ATLAS fades into deep space, the debate will end. But the questions it leaves behind could redefine our understanding of life, matter, and cosmic intent itself. The scientific community may soon be left with more questions than answers, and no second opportunity, the black swan of astronomy. When historians look back on the year 2025, they may call the arrival of 3I/ATLAS not an event, but an inflection point, a moment when modern astronomy confronted something it could neither explain nor dismiss. No single anomaly defines the danger or the wonder of 3I/ATLAS. It's the cumulative weight of every contradiction, the negative polarization, the unmatched resilience, the improbable trajectory, and the unexplained data blackout, each stacking upon the last like layers of cosmic defiance. Together, they form what researchers now call a black swan event, an occurrence so improbable, so disruptive, that it forces a complete reevaluation of everything science thought it knew. At its core, 3I/ATLAS is not just another interstellar visitor. It is a crucible for scientific humility, a reminder that the universe still holds surprises powerful enough to shatter decades of consensus. Among the most vocal analysts is Dr. Avi Loeb, the Harvard astrophysicist, who first suggested that Oumuamua might have been artificial in origin. Now, he estimates a 30 to 40% probability that 3I/ATLAS is not entirely natural. That's not a fringe claim. It's a grounded mathematical assessment based on its trajectory precision, mass distribution, and resistance to solar forces that would have destroyed any known comet. Loeb's reasoning is unsettlingly logical. If you wanted to observe planets efficiently, he notes, you'd pick a trajectory just like this, aligned with the ecliptic, optimized for flybys, and timed to gather maximum data without attracting attention. From an engineering perspective, every element of 3I/ATLAS's behavior makes sense. From a natural perspective, it borders on impossible. Yet not all agree on the artificial hypothesis. Dr. Suzanne Fenner of the European Southern Observatory proposes a radically different vision, one that's no less awe-inspiring. She argues that 3I/ATLAS may not be a probe, but a planetary seed, a fragment ejected from the violent birth of an ancient star system, carrying organic molecules and prebiotic material across the galaxy. If her hypothesis holds true, this interstellar wanderer could represent the mechanism of cosmic panspermia, nature's own way of spreading the ingredients of life between the stars. Captured by young systems, such objects could ignite the spark of creation, transforming sterile worlds into living planets. Either way, artifact or embryo, 3I/ATLAS forces humanity to face the same haunting question: what else is out there? As it hurtles away from the sun, accelerating toward the outer dark at over 55 kilometers per second, our instruments will soon fall silent. The faint glow of its coma will fade, the spectral lines will vanish into the cosmic background, and all that will remain are the fragments of data and the echoes of speculation. For scientists, it marks the end of observation. For storytellers, perhaps, it marks the beginning of a legend, because whether 3I/ATLAS is a Trojan horse, a seed of life, or something we cannot yet imagine, it has already changed us. It has reminded us that the cosmos is not a closed book, but a living manuscript still being written, one page of mystery at a time. And somewhere beyond the reach of our telescopes, 3I/ATLAS keeps moving, silent and indifferent, carrying within it either the story of our beginnings or the echo of another civilization watching us from the dark. 3I/ATLAS is not just an object moving through the solar system, it's a messenger. A fragment from the epic of planet formation carrying the raw materials and chemical fingerprints of a vanished star system. Every grain of dust it sheds, every spectral line it leaves in our instruments, tells a story that predates our sun itself. Whether it is artificial or primordial, one truth remains. 3I/ATLAS forces a rewrite of what we thought was possible in planetary science. Its implications ripple far beyond astronomy. If it is artificial, it would be the single most consequential discovery in human history. Proof that intelligence has crossed interstellar distances, perhaps long before we learned to look up. It would mean we are not alone, and that contact, in some subtle and distant way, has already happened. If it is natural, the revelation is no less staggering. It would mean the galaxy is far more dynamic, fertile, and unpredictable than our models ever imagined. A place where massive interstellar bodies can cross the void, carrying exotic chemistry and possibly the building blocks of new worlds. The Black Swan label isn't just poetic hyperbole, it's a scientific warning that this encounter exposes the limits of our preparedness. The next interstellar visitor may arrive faster, brighter, or closer. It could be harmless or transformative. Right now, humanity's readiness to confront such cosmic anomalies remains untested. In the end, 3I/ATLAS is a test of nerve, a challenge to our confidence in the known laws of the universe. It demands new theories, new observing strategies, and a willingness to embrace the unknown without fear. Whether it proves to be a Trojan horse, a planetary seed, or something stranger still, one fact is undeniable. It has expanded the horizon of the possible. From the first hint of negative polarization, to the solar storm it survived, to the NASA data blackout and the haunting precision of its trajectory, this countdown has revealed why 3I/ATLAS stands apart from every interstellar object ever observed. Across all 10 anomalies, a single pattern emerges: extreme composition, unmatched stability, improbable origin, perfect alignment. No model explains them all, and that's exactly why it matters. Because in a universe as vast and ancient as ours, impossibility is never permanent. Every mystery we solve leads to a deeper one. Every black swan becomes the dawn of a new chapter in discovery. So tonight, as 3I/ATLAS drifts silently beyond Jupiter's orbit, fading into the darkness between stars, it leaves us with one lingering question. What if this wasn't the first time something has come to look at us, and it won't be the last? The answer, somewhere out there, is still traveling, quietly, endlessly, toward another star. The cumulative scientific impact is undeniable. 3I/ATLAS isn't just rare, it's a black swan event, one that has forced astronomers to rethink everything they believed about interstellar visitors. Whether it is natural or engineered, its staggering mass, resilience, and cosmic precision break the limits of old models and demand entirely new theories. The story of 3I/ATLAS reminds us that our solar system is far from ordinary, that even now it can shock, challenge, and redefine our place in the cosmos. And perhaps most unsettling of all, it suggests that the universe may be far stranger and far more closely watched than we ever dared to imagine.